Hello, friends and dear students. So, in this short video on machine dynamics, we will start with the first module, static force analysis. So, what do you mean by static force analysis? How it varies when compared to the one more analysis called the dynamic force analysis. A brief introduction to inertia forces and also what are the conditions for static force analysis. So this is a short video. I'll be explaining to you the static force analysis concepts by some simple worked out examples. As you already know, I'm sure that you may be aware that we have to use a mini drafter or a set square, compass, a mini geometry box in order to work out the problems. So we'll be analyzing how the forces are acting. We are going to determine the magnitude and as well as the direction of forces on various mechanisms, say a 3-bar mechanism, say a two link mechanism, and so on, or a 4-bar mechanism. So the aim of static force analysis is we're going to determine how the forces are acting on a body or an object which is under static equilibrium conditions. So we'll start with the inertia forces. So inertia forces are produced due to the mass and as well as the acceleration of the components. Generally in static force analysis, the magnitude of the inertia forces are usually neglected, because when the inertia forces, the magnitude of the inertia forces are very feeble, then they may be neglected. So under these conditions, static force analysis is done. So static force analysis is carried out when the effect of the inertia force is not going to affect the working of the mechanism. Whereas in dynamic force analysis, we will be considering the inertia effect due to the mass of the components when it accelerates. So this is the main difference between static force and a dynamic force analysis. And when the inertia force are neglected in comparison to the externally applied load, one may go for static force analysis. If the body is under equilibrium condition, then this equilibrium is known as the static equilibrium. And this condition is applicable in many machines, especially say examples are given like clamps, latches, support linkages, and many hand operated tools such as pliers and cutters. So in these cases, the effect of inertia forces may be neglected. Another example is given in the case of say lifting cranes, maybe a hydraulic crane. The bucket load and the static weight loads may be quite high relative to the dynamic forces due to the acceleration and the acceleration of the components as well as its mass. So hence one may go for static force analysis. So in static force analysis, the inertia forces are not considered, whereas in dynamic force analysis, inertia forces, or that is the magnitude of the inertia forces, are considered. Okay, now we will talk about what do you mean by applied and constrained forces. So when you say a constrained force, when two or more bodies are connected together to form a group or a system, the pair of action and reaction forces between any two of the connecting bodies is called the constrained forces. So it constrains the body to move in a particular in a specific manner. So these forces constrain the connected bodies to behave in a specific manner defined by the nature of connection, and forces acting on this system of bodies from outside the system is called the applied force. So the external forces are the applied forces, whereas the constrained forces, it constrains the movement of body in a particular or in a specific manner. And even the electric, magnetic and gravitational forces are example of forces that may be applied without actual physical contact. I think this is quite understandable, but most of the forces we are concerned in mechanical equipment occur through direct physical or mechanical contact. Okay, so static equilibrium conditions. So three examples are given here. These are the forces F1 and F2 acting on an object. See, these are, I think if you go through these figures, you'll be able to understand that this talks about the line of action of forces. So force F1 and as well as F2. So the object in C, in figure C, we'll be able to easily understand that this object is in static equilibrium, because the line of action of F1 and F2, they meet, they have a common line of action. So that is what is being said here. A body is in static equilibrium if sigma F is equal to 0, that is the vector sum of the forces acting on the body is 0, that is F1 plus F2 is equal to 0, and not only that, even the vector sum of all the moments about any arbitrary point is also 0, that is sigma F and sigma M must be equal to 0. Both forces are equal and opposite. See, both these forces are equal and opposite, and their line of action must coincide. So if forces are equal and opposite but not collinear, say in this case it is not collinear, and also here also it is not collinear, and the body may not be in a static equilibrium. See, in this case, since the force F1 and F2 will cause a turning moment, because they are not collinear. Line of action of F1 and F2 in this case is not collinear. See, here it is collinear, so we call this a static equilibrium. And one more example is given of a 3-force member. So though F1 and F2 they meet at a point O, the force F3 doesn't meet at a common point. This point is called the point of concurrency. Whereas in figure B, this object will be in a state of static equilibrium. The reason is F1, F2 and F3 they meet at a common point. So a 3-force member will be in equilibrium if the vector sum of all these forces is equal to 0, and to satisfy the vector sum of all the moments about any arbitrary point equal to 0, their line of action should meet at a common point. This is the point, and you call this as a force polygon. See, the force polygon forms the basis for working out static force analysis problems. You will be seeing that in a number of examples. You call this a force polygon. Then a free body diagram. In free body diagram, you separate a link from the entire mechanism and you analyze how these forces are acting. So that is what being said as if a free body diagram is a sketch or drawing of the body isolated from the rest of the machine and its surroundings, upon which the forces and moments are shown in action. So if you have a 4-bar mechanism, you separate a particular link and analyze how the forces are acting on a particular link that we have selected. Okay, now we will see a member with 2 forces and a torque. So what are the static equilibrium conditions? The forces are equal in magnitude, parallel in direction. See, this F1 and F2, they acting on this link, and there is also a torque that is moving this link. See, this torque T, which causes a turning moment. So what are the conditions? When this particular link will be in static equilibrium, the forces are equal in magnitude, parallel in direction, opposite in sense. That is opposite in direction. The other one is the forces form a couple which is equal and opposite to the applied torque. So this T, applied torque, must be equal to the product of F1 into height. So this is the height. This height between F1 and F2. Mind you, this height h is not the length of the link. This height is the height that is between the. So when you extend this line, F1 and F2, the distance between the line of action of F1 and F2 is the height h. So the product of F1 into h is equal to F2 into h gives a static equilibrium for a member acted upon by 2 forces and a torque. And T is clockwise, whereas the couple formed by F1 and F2 is counterclockwise. So when this happens, the link will be in a static equilibrium. So normally in most of the cases, the above conditions for equilibrium of a member are found to be sufficient. However, in some problems it may be found that the number of forces on a member is 4 or even more than that. So we will be seeing this example in the upcoming slides. Now we will start with this. So as you can see, this is the given diagram. These are the given datas. You have F1, F4 and F2, known in direction, whereas F1 and F4 is known both in magnitude and as well as in direction. We are supposed to determine the magnitude of the force F3 and as well as its direction, and also the magnitude of F2. Okay. So this is a quaternary link. That is, you have these are four links: AB, BC, CD, and AD. Under the action of forces F1, F2, F3, and F4 acting at A, B, C, D respectively, the link is in static equilibrium. Determine the magnitude of forces F2 and F3 and direction of F3. Okay. Now we will proceed by drawing a diagram, that is AB, based on the given data. And also, so you first you draw AB and AD, and using a compass you have to mark C, that is 25 mm and 30 mm, so that we have to make an arc from here. We make an arc, and also from here they will there is the meeting point of the arc. You have to extend DC and BC. Thus you will be able to draw the link 25 mm and as well as 30 mm. Fine. Now, since we do not know the magnitude and direction of F3, we know only the direction of F2. So draw F2 based on the given data, that is 30 degree. When you extend this from here, it must be 30 degree. And similarly, you can mark the direction of F1 and as well as F4. Now here, extend F1 and F4 such that they meet at a point O. Now, based on this, we have to draw what we call as a force polygon. Now, draw using a mini drafter or a set square. Draw F1. Draw this F1 exactly parallel to this line. So how will you draw this? Initially you have to assume a particular scale. Say F1 is equal to 200 Newton is given. You can assume as F1 is equal to say 2 centimeter is equal to 50 newtons. If that is 2 centimeter 50 newtons, so you'll be getting approximately how much? 2 centimeter is equal to 50 newtons. So you'll be getting somewhere around 4 centimeter. Yeah. So this will be 4 centimeter. And similarly 300 newtons based on the assumption. Now draw BC. So initially you drew AB parallel to AO here. Now draw BC exactly parallel to DO, this line DO. So extend this, and when you close this polygon, this forms the resultant force F. So this line, draw a line exactly parallel to this. Yeah. So you have to bring the mini drafter from here, move it towards point O, and then draw a line parallel such that this line is parallel to this resultant force line, that is AC. So you call this a force polygon. So after drawing this, yeah, you see after drawing, okay, so it meets at this line F meets at O, and then extend this line. So when you further extend this line also, they both meet at point say O dash. So when you join this line, the O dash with C, you will be able to get the direction of C, force F3 acting through C. So this is the line of action of C. O dash represents the line of action of force F3, and it was found around 15.5 degree. Okay, now how to find the magnitude? Similarly, you have to draw the force polygon which we drew earlier. So this is again self-explanatory. See, this is AD. So this line will be parallel to this line, and this line will be parallel to this line. So then convert it into the into a particular suitable scale. Remember, we assumed 2 centimeters is equal to 50 newtons. So when you measure this line, you will be able to find out what is the magnitude of F3, and as well as if you measure this line, you will be able to determine the magnitude of F2. Thus the sum is solved. So I repeat again. So you draw there is AD and AB, and from B and D make an arc, complete this diagram, and then extend the line such that F1 and F4 it meets at O, and then based on this draw a force polygon to a suitable scale, and then the closing side will be F. So draw a line parallel to this resultant force line F such that they meet at O, and then extend this line such that this F2 line of action of force of F2 and the line of action of resultant force F meets at O dash, and then join this link, join C with O dash. So thus you will be able to find out the direction of F3, and as well as based on this you have to draw another force polygon just by joining, continuing from here, the F3 that is parallel to this, and then this DA parallel to DA parallel to this, and F3 parallel to this, and take the suitable scale and then convert it into in terms of newtons. You will be able to find out what is the direction magnitude of F3 and the magnitude of F2. That's all.